Today we're going to talk about quantum numbers. And as you're going to see, we will use these quantum numbers to construct electron configurations. Your electron configuration video is your homework for tonight. So you will see that these quantum numbers are playing a big part in those electron configurations. So we're just going to scratch the surface and learn a little bit about quantum numbers. So our learning target is to identify a diagram or model of an atom. That's going to be these configurations that we start tonight, continue on with tomorrow. We're going to diagram each individual element. Now, what are some success criteria that we need to do to achieve that learning target? Well, first of all, we need to be able to identify the 4 different quantum numbers. We need to be able to explain the concept of atomic orbitals. We also need to recognize that these orbitals are of the S, the P, the D, and the F variety. So we have 4 different types of those orbitals, which we're going to call sublevels. So the quantum numbers, I'm just going to list all of the quantum numbers here, and then we're going to go a little bit more in depth on them. The very first quantum number is the principal quantum number, principal quantum number, and we represent that by a lowercase n. At times you'll hear me ask, what is n? What is n? That means the lowercase n, the principal quantum number. It describes the size of the orbital or the energy level. I tend to call these energy levels. So if I say, well, what's your main energy level? I'm talking about this, the principal quantum number. Next is the angular quantum number, lowercase l. I refer to these as sublevels. Sublevels. These sublevels describe the shape of the particular orbital. The third is the magnetic quantum number, and it describes an orbital's orientation in space. What do I mean by that? Well, stop and think about this as a graph. Okay? We have an x-axis, we have a y-axis, there could be a z-axis if it were in 3-dimension. Okay? We're going to talk about the p orbitals in terms of those different orientations. Now, with the d and the f orbitals, I'll show you pictures of those a little bit. I'm not so concerned that you know those orientations, okay, because they're pretty complex. But the p I don't think is too tough to go through, so we'll talk about the p orbitals and the different orientations. And finally, the spin quantum number, which describes the spin or direction in which the electron is spinning. Okay, I've seen this represented in a couple of different ways, and I'm going to show you one way, but just think of it like this. If one of the electrons is spinning clockwise, the other spinning counterclockwise. It's just going the opposite direction. Okay? Now, with these 4 quantum numbers, no 2 elements have the same 4 quantum numbers. They could have 3 out of the 4, but if they had the principal, angular, and magnetic quantum number are all the same, then the spin would be different. Okay? So no 2 elements have the same 4 quantum numbers. Principal quantum number is signified by the lowercase m, like we said. You'll hear me talk, and I don't usually call this the principal quantum number. I call it the energy level, or it might be called the principal energy level. All right. This is describing how far away from the nucleus the electron shell or the level is. So, the lower the number, the closer the energy level is to the nucleus. The higher the number, the further away. Go ahead and take out your periodic table. I want you to look. We have already numbered the periods on the periodic table, didn't we? 1 to 7. Wow. Fancy that those same 1 to 7 are dealing with the principal energy level. So those are our 7 energy levels that we're going to deal with. Obviously, 1 is the lower number, so it is closer to the nucleus than what 7 is. The maximum number of electrons that can fit on an energy level is given by the formula 2n squared. Okay? If we're dealing with the first energy level, n is equal to 1. So n squared, 1 squared is 1, times 2 is 2. So the first energy level can only hold 2 electrons. The second energy level, n is equal to 2. 2 squared is 4. 4 times 2 is 8. So there could be 8 electrons on the second energy level. Okay? So on and so on. 3, third energy level. 3 squared is 9 times 2 is 18. So I could go on and on, but I think you get it by now. Okay? That's not too tough of math. Now, I told you before, you'll see this, PEL, okay? When you see PEL, that is the principal energy level. So if I talk about the PEL, you'll know what my terminology is. We're talking about that main energy level, the principal energy level, or principal quantum number. Here is a diagram. That's why I skipped through that other one real quickly, because I'm looking at this and I say, okay, here is an S sublevel, okay? The first S, first energy level, an S sublevel. Second energy level, an S sublevel. Third energy level, an S sublevel, okay? Our next one is the angular quantum number, which I refer to as a sublevel, okay? What is the sublevel? Well, the sublevel determines the shape of the orbital. And we're dealing with these. We deal with 4 different types. And those 4 types are the S orbitals, the P, the D, and the F. So the 4 types of orbitals, the S, P, D, and F orbitals. If you look at these are going to show you the next one we're going to talk about, some orientations, all right? But I want you to look at these. I told you that when we get into the P's, okay, we can do the PX, okay? See, that's on this X arrow right there. Here's the PZ, okay, because that's on the Z axis there. Here's the PY right there because it's on the Y axis. So I don't think those are too tough, the PX, the PY, the PZ. But if you look at these, okay, these all are more complicated, okay? More complicated. So this one is going to be something like the DX2Y2, okay? So those are a lot more complicated when we're naming those, so we're not going to worry about those. But the main thing, and look at these F's, they're even more complicated, all right? They're even more complicated than the D's. The main thing that I want you to worry about these as far as this diagram is numbers, okay? Look here, here's the S. There's only 1 orbital, right? Here's the P's. How many are there? 1, 2, 3. Here's the D's. How many are there? 5. Here's the F's. How many? 7. 1, 3, 5, 7. So the S has 1 orbital, okay? The P sublevel will have 3 orbitals. The D sublevel will have 5 orbitals, and the F sublevel will have 7. That's the main point you have to remember off of those. Our magnetic quantum number, okay, lowercase m, or orbitals. We just talked about those orbitals, right? Tells us how many orbitals there are of a particular type and their orientation. The px, the py, the pz. That's what this magnetic quantum number is. Now, with each orbital, it can hold 2 electrons. So since there's only one s orbital, how many electrons can fit on the s orbital? 2. How many p orbitals did we have? 3 times 2 is? So we can have 6 electrons on p. How many electrons on the d? 10. How many electrons on the f? 14. Once again, some pretty tough math, right? Pretty tough math. So, if we look at this right here, here is an s orbital. Here's an s orbital. The 2 little yellow dots there are representing the 2 electrons that are on that s orbital. This diagram shows the 3 different p orbitals individually, then together. This right here is a px orbital. So I see my 2 electrons on the px. Over here is the py orbital. Can't see that. That says py right there. Here's my 2. Here is the pz. All right. Here's my pz. There's my 2. And then when I put all of my p's together, I know that the entire p sublevel can hold 6 electrons. My final quantum number is the spin quantum number. With the spin quantum number, the number specifying the direction of the spin of the electron around its own axis. We said that each orbital can hold only 2 electrons. So on that orbital, the electrons are spinning in opposite directions. So if I look at this, this is somehow how we represent orbitals by squares. So this to me is the 1s orbital. So the 1s orbital here has 2 electrons on it. One spinning this way, one spinning the opposite way. So that's how we signify the opposite spins. Okay? Here's 1 electron. I can see there's only 1 arrow. So there's only 1 electron on this s orbital right here. Here's 2 electrons on this s orbital. All right. So basically, like I said, I just wanted to introduce you today to the 4 different quantum numbers so you recognize them. We are going to put this together big time because you're going to watch the electron configuration video tonight, and then you are going to make some electron configurations tomorrow, and we'll bring together how these quantum numbers help us with the electron configuration. Okay?